Oh, hi everyone. So I'm Carys and I'm a first year PhD student studying the South Pole-Aitken basin at Imperial College London. And fortunately for me, James Keane introduced the basin really nicely first thing this morning. And it's definitely an exciting time to be studying the SPA. As we've seen already this week, there's a lot of missions heading to this region on the moon. So yeah, it's a cool topic to be studying. And there are a lot of unknowns regarding the SPA basin. So for example, its age. Hopefully we might get a constraint on that within the next few months with the sample return from Chang'e 6. There's also a lot of current debate regarding the impact direction. So whether it went from north to south or south to north. That's something that needs to be answered. There's also some questions regarding the lunar highlands up here to the northeast of the basin, and whether that might be SPA ejecta. And there's also some recent work looking at whether actually it's not just an ellipse, but a tapered ellipse. And if so, that might also help us constrain the impact direction. And then there's also some previous work that's looked at the antipodal and global effects, because this was a truly large impact event with big implications for the evolution of the moon. So yeah, there are a lot of things that we still need to understand regarding the SPA basin, and we can try and address some of these things through numerical modeling. So previous work has modeled the SPA impact event in both 2D and 3D. So in Potter et al. 2012, they modeled the impact in two dimensions and found a best fit scenario using a 170-kilometer diameter impactor, a 10 kilometer per second velocity, and a hot 50 Kelvin per kilometer thermal profile. And that generated a crater most similar to observations and previous estimates. And then in 3D, more recently, Milosh et al., they used very similar impact parameters, but then they used a cold profile of 10 Kelvin per kilometer and an undifferentiated projectile and crystallis moon. And they showed that the mantle could be exposed during the impact event using 3D modeling. And then more recently, Tom Davison et al. At Imperial, they modeled the SPA impact using a differentiated moon and projectile and made this quite nice animation here. And they showed that the impact angle, velocity, and target thermal gradient have a strong influence on the spatial distribution of ejecta, depth, and volume of excavated material. And that's the work that I'm building on during my PhD. So we've been conducting a number of simulations varying different parameters such as the impact angle, the velocity, and the thermal profile. We've been using a 5 kilometer per cell resolution and a 20 CPPR. We're using multiple distinct materials, which are currently the best available analogs in ISAIL. We're using Lagrangian traces to track the ejected crust and upper mantle, the fate of projectile, and deformation of the subsurface. And then we're running our simulations up to 3 hours post-impact. We're then processing and comparing our outputs to observational constraints from lunar spacecraft data. And currently, our best fit scenario is a scenario here on the right, where I've made an animation here. And that's the 30-degree hot scenario. And hopefully, over the next few slides, you'll see why that is the case. So here, I've got some snapshots, just in case the animation didn't work. But I'm going to assume that not too many people here study impacts. So here is the impact process in a bit more detail. So on the top left here, we're about 100 seconds into the simulation. And you can see that the ejector curtain is going here downrange. So the arrow's gone missing, but the impact's going from the right to the left of the screen. And within about 5 minutes to the second image here, the transient crater is formed. And that's roughly 1,000 kilometers in diameter, which is consistent with previous estimates. And after that, the center of the basin starts to uplift, so that basin floor rebounds, and it all uplifts, just like you can see by the black arrow here. And within about 2,000 seconds, we hit the point of maximum uplift. You can see that, if you look carefully, you can see that the crust is thickening due to that uplift. And then after about 4,000 seconds, you can see that uplifted center is all collapsing in again. And that causes the crust, which I've shown in the green arrows, to thin and thicken. So it's thinning inwards and thickening outwards. And that continues beyond 3 hours. So you can see that even after 3 hours, it's not completely settled down. You can still see that the crust is thickening out almost like a rippling pattern outwards. Also interesting to note is that this dark material inside is projectile. So the projectile material is mixing in with the mantle and ending up underneath the basin. And then here you can see that the mantle has been exposed in the middle of the basin. So we processed our results and have looked here at the crustal thickness. So on the left here, just like David was talking about in the previous talk, we've used the Grail data processing of the thickness, and we've adjusted it by the average crustal thickness. So in the center of the basin, it's thinner than the average, and outside the basin in red it's thicker than the average. And then with our simulation results, we're showing the change in crustal thickness due to the simulation. So in the middle in blue is our thinner crust, and outside in red is our thicker crust. And it's not showing up too well on this screen, but it might be showing better. It's showing better on the smaller screens. You can see that where it goes from blue to red is a lot more consistent for the 30-degree scenario versus the cold scenario. But what you can see on the screen is that in the cold scenario, it generates this big, thick red rim around the crater, which you can't see in the observations at any distance around the crater. So that's inconsistent. Also, you can see that in the middle of the crater for the cold scenario, it's really dark blue. So the whole crust there has been excavated and removed. And that's not consistent with observations either. But you can see in the hot scenario, it does remove the crust a little bit in the middle. So you can see here, right in the center, that the mantle has been exposed. And we do need to run the simulation a bit longer because it does seem to be shrinking in size in the middle. But we expect that potentially the crust there's differentiation of the melt pool, and it's generated a secondary crust in the middle there. You can also see that this hasn't completely settled, even though we've been running it for 3 hours, because it's not consistent at the surface here. And you can also see that where it's thinning, and the crust is thinning, is actually quite consistent with observations. So we're quite happy with that. And you can see that as well when we just look at the crustal thickness. So when we look at the hot scenarios, it's a lot more consistent than the cold scenarios. And importantly, it's these regions here where the crust has thickened. They're not disappearing when we run the simulations for longer. So yeah, they're pretty inconsistent with observations. And so there must have been some sort of weakening due to the hot crust, or because our crust is hot, it's weakening the crust and not generating these thick rims. So that's why we prefer the hot scenarios. However, there's a problem. The lunar far side was likely to be cooler than 50 Kelvin per kilometer at the time of the SP8 impact. So here on the right is a figure from thermal models. And if we do a conversion between 50 kelvins per kilometer to a surface heat flow, we're way off the chart here, up here somewhere, or beyond that. So our 50 Kelvin per kilometer model is likely too hot compared to thermal models. We also know that it's likely that the mantle was excavated, which means there's probably some sort of stratification. There's also been a proposed magma-ocean dichotomy across the middle of the basin. So all of that would be molten, and then that was solid, which is a nice coincidence that we want to look at a bit more in detail in future work, which might suggest that actually we'd be looking at somewhere over here for our thermal profile and not way up there. So question is, how do we then generate a weaker crust, but without a 50 Kelvin per kilometer profile, so that we don't generate these rims of material which are not consistent with observations? And that's a potential for that is to include acoustic fluidization in our models. And so acoustic fluidization can weaken the crust and hopefully generate results that are more consistent with observations without needing such a hot temperature. And that's been incorporated in 2D, but we're looking to incorporate that in 3D in future work. So now let's look at the ejecta distribution and the implications for that. So here are results for the 30-degree hot scenario, and we've shown it in both trajectory directions, as we're not ruling out either yet. So we've modeled our ejecta using ballistic projections. You can see that the thickest distribution is around the rim of the crater. Whoops, that's a spoiler alert. And you can see that it generates a roughly bilaterally symmetrical pattern, which is also interesting when you consider proposals that the far side's highlands might be SP ejecta, because that's all just on one side, but our projections show that it's pretty symmetrical on both sides. Our volumes of ejecta are pretty similar to previous work, so that's, thank you, that's reassuring. And then you can also see that there's a bit of a forbidden zone being formed, both downrange and uprange. And in particular, you can see that for the mantle. So for the mantle, you can see that it's roughly between 9, 11 o'clock and 1 and 3 o'clock. And there's no mantle being ejected to the north of the basin or to the south of the basin, which is really interesting when you compare it to proposals that the thorium anomalies that have been observed around the basin might be due to mantle ejecta. So the center here is probably mantled due to the collapse of the central uplift, and that's then been placed on the surface. But this lobe here could all be mantle ejecta. That's interesting to compare to the mantle locations in our models. And then it's also interesting to compare it to where we've got locations that hopefully will bring back samples. And if either of these bring back samples of the mantle, it might help us constrain the impact direction, which is exciting. So to conclude, our current best fit scenario is a 30-degree, 50 Kelvin per kilometer, 200 kilometer diameter impactor at 10 kilometers per second scenario. And the key reasons for that is that the narrow rim of material that we produce in our crustal thickness maps, that's just not seen in observations. But there is a problem because 50 Kelvin per kilometer does seem that it is likely too hot. And then for our ejector, it produces a butterfly pattern at 30 degrees, and in particular for the mantle, the location, the trajectory direction has implications for where we might find SPA ejected mantle. So yeah, I'm excited to be working on this for the rest of my PhD. I've got lots of ongoing and future plans. So of course, lots of more simulations are planned to help constrain the parameters further. We're looking to put a pre-impact crystal thickness model and thermal dichotomy in the models to see how that affects the resulting crystal thickness and ejector distribution. We're looking to put the acoustic fluidization in 3D to see if that can allow us to use a cooler profile. And then we're also going to look further into where the SPA ejector is located to help us hopefully constrain the trajectory direction and the relationship with the lunar highlands. Thank you.
Are there any questions?
Do you have to have any particular symmetry in your solution, or does it matter whether you're going north or south in the calculations you're doing?
So the simulations themselves, we're then orientating our outputs and to the south or north. But I think if we put a dichotomy in there, then it will have an effect on which way we run the simulation. But at the moment, we can all do it post-processing, deciding which way we want to run it.
Thank you. Great talk. Maybe you said it and I missed it, but what type of impactor did you use in these simulations?
So it's a differentiated impactor with an iron core. And yeah, the iron core is pretty important because that has an effect on the impact energy.
Right. Thank you. Thank you very much for your very nice piece of work. If you were a bit less cautious or careful with your results, would you be ready to gamble and tell us whether you prefer the northward or southward trajectory direction, or is it impossible to discriminate? What's your feeling?
I think as a group, we're trying to not choose yet because there are arguments for both that are plausible. But I think once we put a dichotomy in there, I think that will be quite convincing of which one it is. So that will give us patterns that either clearly support one direction or not. I think, yeah, we're being careful at the moment not to choose one and keeping an open mind because there are arguments that seem plausible for both directions.
Okay, thank you.